Good afternoon, everyone. I am Dr. Deepa Philip from IIT Kanpur, and this is the course titled Artificial Intelligence in Industrial Management Engineering. This is being offered as part of the NPTEL MOOCs basket offered from IIT Kanpur. Along with me, Dr. Prabal Pratap Singh is also co-teaching this course, and we are in the week 4, and we have been looking into the importance of sorting and searching in AI, and why it is critical to developing various AI systems. So, we have seen what we call as blind search or uninformed search so far, and yesterday the previous lecture, when we were closing the lecture, we talked about how we can add problem specific, domain specific information into the search to determine which is a good to determine which node to branch upon. And if you remember yesterday's lecture, the last slide we talked about was a greedy best first search algorithm, and the straight line distance, that was the heuristic that was used. Okay. So, today what we will try to do is we will try to create a, let us talk about a bad example, greedy search. Okay. The question that we had yesterday was, it rapidly finds the optimal solution. Does it always finds the optimal solution rapidly? So, let us take a look at a network. Okay, for the time being, you have a network starting at A, start state, okay. Then we have B, okay, and the time unit is 7, okay. And then you have D here, okay, and E, okay, and you have F. So, it is part of that network that we took yesterday out, okay, and this distance is 6, this is 3, 4 and 4. Okay. So, this is the network A, B, D, E, F, okay. And also we say, let us say that the heuristic that we talked about yesterday, okay, the H of A, okay. Oh, by the way, your goal state is F. So, the aim is to go from A to F. So, H of A is equal to, this is 9, this is straight line distance. H of B is equal to 5, H of C is equal to, there is no C, H of D is equal to 6, H of E is equal to 3, and H of F is equal to 0. Okay. So, if you remember yesterday's lecture, we have talked about H as the straight line distance. Okay. H stands for the heuristic. So, this is the straight line distance. Okay. This is a straight line distance, okay, heuristic. Now, the starting point is, if you remember the previous evaluation, the state is A and the cost is 0 and H is 9. So, let us try to expand this network. Okay. So, the start node is, so this is the begin, which is the state is equal to A, then the cost is equal to 0, H of A, or let us say H, the heuristic, is equal to, in this point it is given as 9. Okay. And from here you can see that we have two branches we can take, B or D. Okay. So, let us do two branches. Okay. This is B or D. Here the state is equal to B, here the state is equal to D. Okay. So, when you go to B, the cost is, you can see that the cost is equal to 7. Okay. And H, what is the value of H here? H of B is 5. Okay. For state equal to D, okay, the cost is 3, equal to 3, and H of D, H is equal to 6. Okay. Now, if you remember yesterday's example, then if you remember yesterday's example, we can see that we will branch on the smaller value, which is a seemingly closer one, right. The seemingly closer one is H is equal to 5, my bad. Okay. So, this is the seemingly closer. seemingly closer. 5 is always less than 6, I am being stupid, that is all what it is. So, from here we branch, which is f, okay. State is equal to f, okay. Cost is equal to 7 plus 6, okay. That is equal to 13, and h is equal to 0 at this point. So, this is your goal state. Okay. So, you reached here at a cost of 15. Okay. So, you achieved your goal state. Okay. So, we reached goal state at a cost of 13. Okay. Now, let us think about what about the other option or other path. So, if we look into that, let us expand that. So, if you expand this from D, you have to go to E. So, E state is equal to E, cost is equal to 3 plus 4, that is 7, and H is equal to 3. Okay. And you expand from here, you have state equal to F, cost is equal to 7 plus 4, that is 11, okay. H is equal to 0, and you have your goal state. Okay. So, if you look into this, this is better than what greedy algorithm found. So, the other option, this is definitely better than what the greedy algorithm found. So, we will find you a goal state, but need not be optimal. The question that we asked yesterday was that is it always find the optimal solution? Need not. Okay. It need not find the optimal solution always. Okay. That is the key takeaway out of this contrived example, to tell you that it need not be true all the time. Then what is the solution to this problem? Okay. So, now let us look into another search which is called as A star search, and in the A star search, let us start with another assumption. Let G of n, okay, be cost incurred already on path to n. Okay. Path to n is your goal. Okay. So, let G of n be the cost incurred already on path to n. Okay. Now, instead of H n, expand nodes with lowest G n plus H n first. So, instead of just taking the heuristic straight line distance, now let us take the combined G n plus H n and then expand that first. Okay. So, let us take our network again, A start state, you have B 7, you have D, that is 3, you have E, that is 4, and you have F, that is also 4, and B to F is 6, the previous network that we talk about. Okay. And we also say that, say H of A is equal to 9, and this is your goal state for that matter. F is your goal state, the previous example. H of A is equal to 9, H of B is equal to 5, H of D is equal to 6, H of E is equal to 3, h of f is equal to 0 and this is your goal. Okay. Now, how do we do this? Instead of choosing on the small, let us do the g n plus h n. Now, the new logic is the g n plus h n. G n is the cost of reaching to state. Okay. So, if that is the case, our starting point is as usual, this is state equals A and then the cost is equal to 0 and h is equal to h of A is 9, right. So, the what we have to consider is the logic that we need to consider is 0 plus 9, that is equal to 9. Okay. So, that is what we will use, the g n plus h n. So, this is your g n, this is your h n. Okay. Now, we have two branches B and D. So, we do it like this. This is state equal to B, okay, state equal to D, the cost is equal to, from here to B is 7, okay. Here the cost is equal to 3 to D, then H is equal to, in this case is H of B is 5, here the H is equal to 6. So, if you only use the H, then we would have branched on B. Now, we have, this is your G n, this is your H n. So, which implies 7 plus 5 is 12, that is 1. In this case is, this is your G n, the cost reaching here, this is your H n, that is 6 plus 3 is equal to 9. So, now when you combine these two, you can find that this is lower value. Okay. So, expand the value with the lowest, we are using that idea. Okay. So, if that is the case, now what do? We expand from here, because this is the lowest. So, we expand, reach here, that state will be state equal to E, okay. Cost is equal to, cost is 4, okay. Not 4, 4 plus 3, that is 7, then H is equal to, H is given as H of E is 3, right. So, it is 7 plus 3, that is equal to 10. Okay. Now, if you compare these two values 12 and 10, you can see that this is smaller, okay, lower value. Okay. Since it is the lower value, what will happen? Now, you will expand on this. Okay. So, the from E you can go to F. So, we come here, state equal to F, cost is equal to 7 plus 4, that is 11, H is equal to 0 and here you reached your goal state. Okay. And the total cost that you reached. Okay. So, the cost of reaching the goal state is lowest here. Okay. So, by combining the cost of reaching that state and also the straight line distance, we are able to get a better value in this case. The question that I would also ask you at this point is, what would happen if all H, if H is equal to 0 for all states? That means, if you do not have this information, okay, the straight line distance, what will happen? Okay. That is the other way you can think about this. Okay. All right. Now, continuing, we will talk about another topic which is called as the local beam search. Okay. And this is another variant of search as part of this, and let us talk about what this is. See, the logic here is that we are just introducing you here. but I would request you to read through that. So, what we do is the keep track of best k states. Okay. Then number 2, generate all successors of these k states. Okay. Generate all successors of these k states. Then 3, if goal is reached, stop. Okay. If not, if the goal is not reached, if not, select the best k successors, and repeat. Okay. So, the beam search is you keep track of k. K is an arbitrary number that you can decide and determine, and you kind of expand the k, and from the when you expand the k, if the goal is reached, then you stop. If it is not, you select the best k successors from the list of successors and you repeat the process. Okay. So, this kind of a search is what we call as the local beam search. Okay. We saw what is an A star search, and we just saw what is a local beam search. I am not going to work an example of this. This is just for your information. Please learn by yourself. Then we talk about a next factor, which is called as admissibility. Okay. And this admissibility is this is of heuristic. Okay. So, we are talking about the heuristic, which is the heuristic in this regard. We talked about the h, which is a straight line distance. Okay. So, let us talk about a heuristic is admissible. Heuristic is admissible, calling a heuristic admissible if it never overestimates the distance to the goal. Distance to the goal. Okay. So, if you call it admissible, you call it as admissible if it never overestimates. We do not want it to overestimate at all the distances to the goal. Okay. So, that means if n is the optimal solution, if n is the optimal solution reachable from n prime, then g of n, okay, should be greater than or equal to g of n prime plus h of n prime. That is the logic. So, if you can reach n, n is the optimal solution which is reachable from n prime or n dash, then g of n, okay, should be greater than or equal to g of n n prime plus h of n prime. Okay. So, second one is straight line distance is admissible. It is admissible. Okay. So, why is this admissible? Because you can't hope for anything better, can't hope for anything better than straight road to the goal. Okay. So, it is an admissible thing, it will never overestimate no matter what, there is nothing better than that. Okay. So, admissible heuristic means that A star is always optimistic. Okay. So, if the heuristic is admissible, that means A star is always optimistic, it will get you where it is. Okay. Then if the heuristic is admissible, if the heuristic is admissible, if the heuristic is admissible, A star is optimal. Okay. If the heuristic is admissible, A star is optimal. Optimal means that it will never return a suboptimal solution. Okay. It will never return a suboptimal solution. Then A star is optimally efficient. Okay. A star is optimally efficient. So, implies, what does that mean? Implies that any other optimal algorithm, okay, any other optimal algorithm must expand least the nodes A star expands. So, that means that any other optimal algorithm that you take, it should also expand, it must expand at least the nodes that A star has expanded, right. The major drawback of A star, what is the major drawback of A star? Space requirement. Okay. What do you mean by space requirement? Similar to that of BFS, breadth first search. Okay. So, the same space requirement, similar space requirement problem as that of breadth first search is also a part of the, that is a big issue. The space requirement is an issue with the A star, but if you look into it, it is optimally efficient and it is also optimal and it is optimistic. Okay. As long as the heuristic is admissible, then A star is optimistic, optimal and efficient. Then let us talk a little bit about how do we design heuristics, okay, and what are some of the strategies are associated with designing heuristics. Okay. And with that we can conclude this lecture. So, the first thing is one strategy for heuristic design. Okay. Relax the problem. Okay. Relax the problem, one of the strategy. What is it? When you say relax the problem, what is it? This means make it easier. In a simple sense, it is called make it easier. Okay. So, that is one of the easiest way. So, like an example is number of misplaced tiles, heuristic corresponds to relaxed problem where tiles can jump to any locations, tiles can jump to any location even if someone else is already there. Okay. So, a specific problem, the tile problem that you all know about. Okay. So, the number of misplaced tiles. Okay. So, that heuristic it corresponds to the relaxed problem, the tiles can jump to any location. The another example is sum of Manhattan distances. Okay. This heuristic corresponds to relaxed problem where multiple tiles can occupy the same spot. So, this is another one, this is another example, another relaxed problem, right. So, the logic here is that the ideal, the key word is this, the ideal relaxed problem is, and just give two examples, that is all what I did. Problem is, the ideal relaxed problem is A, easy to solve, B, not much cheaper to solve than original problem. Okay. So, the ideal relaxed problem, it is easy to solve, that is the first one. It is not much cheaper to solve than the original problem, cheaper in the sense of computational requirements and another things. Okay. Then the last part is, some programs, there exist programs can successfully and automatically create heuristics. Okay. There are certain programs that can successfully and automatically create heuristics. Okay. That options are also available as part of this. So, we briefly looked into what we call as how do we design the heuristics, and also some of the strategies that you can use, like relaxing the problem, and some of the relaxed problems like the number of misplaced tiles or sum of Manhattan distances, etc. So, with this we have now seen, or we are come across the basic aspects of searching, and we looked into multiple search algorithms, both informed and uninformed search, and we also saw how this is an important aspect, how sometimes the search process with problem specific domain can be made better. So, hopefully you guys will take on this, read forward, build more capabilities, understand more things, and then implement this using whichever programming language you are comfortable with. So, thank you for your patient hearing, and Dr. Prabal Pratap Singh should be teaching you guys how to implement some of these complicated aspects associated with the such kind of search problems. Thank you for your patient hearing.